Good morning, good morning, good morning, good morning. So let's go ahead and do some question answer. सवाल हमारे जवाब आपके. So we are in the third chapter of mechanics, and in the third chapter of mechanics, first one was laws of dry friction, second one was sliding, third one was toppling, fourth one was belt friction, and here we go with the fourth application, and the fourth application is power screw. If you remember last session of power screw, we actually built a lot of things. Wait a moment. So we are at the application number 4, power screw. And in previous session, we have done some, what do you say, homework to study power screw. That homework was, the first part of the homework was that suppose a block is kept over an inclined plane of angle theta, block of weight W. Then how much force we will have to apply in positive x direction to move the block up the plane. So the force F required, or the force P, we actually denoted it as P. So the force P required, the force P required to, more precisely, horizontal force P required horizontal force P required to move the block horizontal force P required to move the block of weight W up the inclined plane of angle theta, up the inclined plane of angle theta, would be how much? Somebody please come forward.
P
And
is
then
equal to
P is equals to
W
W10
tan
phi
of
s plus theta.
phi s plus theta.
W tan
Phi s plus
phi
theta.
phi s plus theta. W tan phi s plus theta. Okay. So there is no phi s I can see in figure. I cannot see any phi s in figure. What the hell is this phi s?
Sure, angle of friction, sir.
Angle of friction?
Angle of repose, sir.
Sorry, sir, angle of friction.
It is the resultant reaction of angle from the normal reaction, sir.
No, it's the limiting value of that angle, isn't it? When you apply a force, friction is going to act, and normal reaction is going to act. Normal reaction is present between two surfaces, and if you apply the force, friction is also going to resist. Friction is also going to resist. Now the resultant reaction will make some angle. Resultant reaction will make some angle from normal reaction. Let's call that angle as phi. Then it's very clear that we can write that angle by the formula tan phi is equal to friction force divided by normal force. Now, if friction force is at limiting value, if friction force is at limiting value, mu multiplied by n, then if friction force is at limiting value, then will become that angle will become tan inverse mu. If friction force is at limiting value, then will become angle phi will become tan inverse mu. All right. So phi is known by the name friction angle, and phi s is known by the name maximum value of friction angle or limiting value of friction angle. Phi is friction angle and phi s is maximum value of friction angle or limiting value of friction angle. Cool. So that's what the friction angle is. That's what phi s is. Limiting value is also known by the name angle of repose. So this was the very first thing we did. The horizontal force P required to move the block of weight W up the inclined plane of angle theta would be W tan phi s plus theta. W tan phi s plus theta. Now, my dear friends, we did one more case, and that case was that there is a block kept here, and I'm now applying a force to move the block down the plane. So once again, we are going to write the horizontal force, the horizontal force P required to the horizontal force P required to move the block of weight W, the horizontal force P required to move the block of weight W down the plane, down the inclined plane theta, or down the inclined plane of angle theta. Down the inclined plane of angle theta. This would be how much?
So W10 theta is minus, phi s minus theta.
This will be W tan phi s minus theta. But this is subjected to a condition. This is subjected to a condition that this formula is valid only if it is known that only if given that phi s is actually greater than theta. That means angle of inclined plane is much smaller. Given that the second case formula is valid only if phi s theta is less than phi s. Why? Or what is the logic behind it? Why this is valid? Why this formula is valid only if theta is less than phi s? Why? Why?
Otherwise,
Then only it
block
will
will
be in
slide
static
down, sir.
condition.
Mm-hmm.
If the
Block
theta
will
is
be
less than
sliding
pi
down.
s, then only it will be in static condition.
It will be fall itself.
If theta becomes more than phi s, then you don't require any force to move it down the plane. It will fall itself. If theta becomes more than phi s, then you don't require any force to move the block down the plane. It will fall itself automatically by its own weight. Its own weight is enough to keep it keep moving it down the plane. So that's why you need to apply force to lower the weight down the plane, to bring the weight to lower the plane down the plane, only if the weight is not automatically coming. If theta becomes more than phi s, weight will automatically start coming down the plane. So I requested you that please do remember both these cases. Number one, horizontal force P required to move the block of weight W up the inclined plane, W tan phi s plus theta, and W tan phi s plus theta, and horizontal force required to move the block down the plane will be W tan phi s minus theta. But the second one is having a restriction that the second one is valid only if theta is less than phi s. The second one is valid only if theta is less than phi s. Now, my dear friends, once we are done with these two things, we are absolutely ready to study power screw. So give me a green signal that yes, now we understand 1, 2, and 3. These three things. Number one, horizontal force P required to move the block up an inclined plane of angle theta, W tan phi s plus theta. Horizontal force required to move the block of weight W down the inclined plane of angle theta would be W tan phi s minus theta. Number three, phi s is what? Phi s is nothing but phi s is what? Phi s is called as limiting value of limiting value of friction angle, and its value is calculated by tan inverse mu s. Keep in mind these three important results. And then we can go ahead and understand power screw. Power screw is actually over. Power screw is done. Once you understand these three things, power screw is actually over, believe me. So let me go ahead and tell you what power screw is very quickly. Let's say this is representing the core body. And then we have got this as the top of the power screw. And then we have got one thread of the power screw like this. This is the first thread. And of course, we have This is how power screw is going to look like. Now, let us understand that this power screw is actually, these are the external threads of the power screw, and these external threads of the power screw is actually fitted in and fitted in internal threads of some kind of a frame. So there may be a frame like this. No, if you think these are two separate parts, you are mistaken. These two are not separate parts. This is only a cross-sectional view. This is actually a round part. 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 Okay. So please don't think of these two things as two separate stands. This is a round part. And in this round part, in that central hole, there are some internal threads. In that central hole, there are some internal threads. Okay. So here you have got some internal threads, some internal threads, some internal threads, some internal threads, in which that external thread of the power screw is fitted. So external thread of the power screw is fitted into it. External thread of the power screw is fitted into it. External thread of the power screw is fitted into it like this. So that power screw external threads are fitted into this frame. And then, my dear friends, at the top, we are having some kind of weight kept over it. At the top, we are having some kind of weight kept over it. I hope now the arrangement is clear. And even though I have represented that weight as a very small box or something, but that weight could be your automobile vehicle. That weight could be the entire truck. That weight could be a big thing. Now, frankly speaking, this whole power screw setup is actually, my dear friends, just the weight either being lowered up an inclined plane or a weight being raised down an inclined plane. I mean, that, please think about that internal thread. That internal thread is like an inclined plane. That internal thread is like an inclined plane, and the screw is like a weight that is being slided up an inclined plane. If you want to raise this weight, and the screw is being slided down that inclined plane if the weight is being lowered. If the weight is being, screw is like a block, and the internal thread on the frame is like an inclined plane. Internal thread on the frame is like an inclined plane. Internal thread is like an inclined plane over which that block in the form of a screw is being slided. When the block in the form of a screw is being slided up the plane, then the weight kept here will be raised. And when the screw in the form of screw in the form of when the screw is being slided up the inclined plane, then the weight is going to be raised little bit. No, weight will go up, 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 and up. And when you rotate the screw in clockwise sense, looking from the top, when you rotate the screw clockwise sense, looking from the top, then a screw will come down and it will be like lowering a block down an inclined plane. Can you please tell me exactly at the inclined plane, exactly at the mid of inclined plane, how much force you need to apply to move the block, how much force you need to apply to move this blue screw block. Screw is, I say it again, that internal thread is like an inclined plane, that internal thread is like an inclined plane of angle theta, and screw is like the block kept over it. And when you are rotating the screw in anti-clockwise sense, you are effectively moving it up the plane. As this screw is moved up the plane, the weight kept over it, the weight kept over it goes upward. We say the weight has been raised. Weight is representing the total weight, by the way. Even though the W is representing the weight of a screw plus weight kept over the screw. I mean, the whole weight is included, but generally the weight of screw itself is negligible in comparison of the weight of car that you are moving up. You remember, no? The screw jack mechanism of car. Screw jack mechanism of car is this only. You rotate the screw. That's it. You rotate and screw in an internal thread. That's it. And the whole car gets lifted. The whole car gets lifted. That's the power of a screw. That's the power of power screw. Okay, that's why we call it power screw. It's a powerful mechanism. So, my dear friends, what will be the force required here? Here means where? Actually, here means some controversy because the block is not, the screw is sitting an inclined plane. Where exactly? The screw is sitting on inclined plane starting between inner radius of thread up to outer radius of thread, up to outer radius of thread. We assume that, let's say, the whole blue screw is kept over that orange internal thread inclined plane. When I say internal thread, it's inclined plane. When I say external thread, it's the block kept over the inclined plane. When I say external thread of screw, it's acting like the block kept over inclined plane, the block kept over inclined plane. And when I say internal thread, it's acting like the inclined plane itself. So because this is static now, here the plane is static now. Here, this blue thing is moving up now. This blue thing is moving up now. Here, this blue thing will be moving up now. So, my dear friends, we have very analogous system present here. We have very analogous system present here. It's totally analogous system. Okay, it's totally analogous system. Dhyan se samajhiyo. It's now we can say the force required at mean radius Rm. Once again, if you want to revise, do revise. The force required to move a block up an inclined plane of angle theta is how much? That is W tan phi s plus theta. W tan phi s plus theta. And the force required to move a block of weight W down the plane The force required to move the block of weight W down the plane, that you calculate as W tan phi s minus theta. W tan phi s minus W tan phi s minus theta. Same formulas are applicable here also. W is present, theta is present, just one little condition we are going to put, that this is the force required at mean radius. This is the force required at mean radius. The force P required at mean radius Rm, at mean radius Rm, to raise the weight W. To raise the weight W. Similarly here, the force P required at mean radius Rm to lower weight W. Okay. Are we really applying a force? We are, since it is a rotating thing, we think in terms of torque. Since it is a rotating thing, screw, so our visualization in terms of torque. So what is the torque needed to raise the load, and what is the torque needed to lower the load? If you are applying this formula at Rm, why are we applying this formula at Rm only? Because when we solved inclined plane with block problem, it was a 2D problem. Now in power screw, we have a 3D thing. So naturally, we will have to assume whole weight concentrated somewhere. And we assume whole weight concentrated somewhere exactly at the average of Ri and Ro. When we solved this block over inclined plane problem, it was a 2D problem. So it was a 2D problem. We never thought that, we thought everything is in the plane of the board only. But in the power screw, it becomes a 3D problem. That 3D problem, my dear friends, it becomes a 3D problem. That 3D problem, my dear friends, we have to assume the whole weight to be concentrated somewhere. And we assume the whole weight to be concentrated at mean of Ri and Ro. At the mean of Ri and Ro, we assume the whole weight to be concentrated at the mean of Ri and Ro. Okay. So that's how Rm comes into the picture. So what will be the torque required to raise or lower the weight W? Torque required to raise the torque required to raise oblique lower weight W using power screw will be how much? That will be P multiplied by Rm. That will be P multiplied by Rm, because you are assuming the whole thing to be concentrated at mean radius. So naturally, torque will be this W tan phi s plus minus theta multiplied by Rm. This is the torque required at mean radius to raise the weight or lower the weight. Raise the weight, you take plus, lower the weight, you take minus. Raise the weight, you take plus, lower the weight, you take minus. Now, are we really going to apply the torque exactly at the mean radius of power screw? No. We are actually generally going to attach a lever or something. If you know how do you operate a screw jack, you attach a lever and then you rotate it, isn't it? So you are going to attach a lever and you apply the force at the end of the lever. This force has been represented here perpendicular to the plane of paper. This force has been represented here perpendicular to the plane of board. This force, yes, has been represented here perpendicular to the plane of paper or perpendicular to the plane of board. So please visualize it in the z-axis, perpendicular to the plane of board. This is the screw, and this is the lever attached at the end of the screw, and this is how the force is being applied. This is the this hand of mine is a screw. Look at this arm here. This is the screw, and this pen is representing the lever at the end of the screw, and then force is being applied perpendicular to that lever like this, so that the screw will be rotated, like cap of a bottle is opened or cap of a bottle is closed. Cool. So we have this F value acting perpendicular to the plane of paper, acting perpendicular to the plane of board. Now, how much torque are you really generating about center? About center, my dear friends, you are generating a torque. Let's say this distance is known to you, and let's say this distance is small a. Then how much torque you are producing about center? The torque that you are producing about center is F into A. So torque that you produce about center is F into A, and the torque that was required was this much. Let me highlight this. W tan phi s plus minus theta, and torque applied is how much? Torque applied is F multiplied by A. Naturally, torque applied must be equal to torque required, otherwise you will not be able to raise the load or lower the load. So torque applied must be equal to required torque. Torque applied must be equal to required torque. So I'm going to write F multiplied by A is equal to W tan phi s plus minus theta, W tan phi s plus minus theta multiplied by Rm. So I'm going to get F is equal to WRm tan phi s plus minus theta upon A. A is the length of lever arm. WRm, and then we have tan phi s plus minus theta upon this total thing upon the lever arm. I say it again, power screw topic was over as soon as you studied these two inclined plane over block over inclined plane problems. As soon as we solved the block over inclined plane problem, that what is the horizontal force required to move a block up an inclined plane, and what is the horizontal force required to move a block down an inclined plane, the power screw topic was over at that time, because that formula and that formula became the formula of power screw. As simple as that. So when you studied that, I say it for one last time, block over inclined plane problem. And we solved it in two manners. Can somebody come forward and tell me how we solved it in two manners? What were those two manners? We obtained
So
this result.
resolution of forces and
Resolution and
method
force and Lamy theory.
forces and Lam's theorem.
Resolution of forces, and another way we followed was three-force principle, Lamy's theorem. Perfect. So let's save this. There are just one or two more things that we need to understand about power screw. And one such thing is that just like the weight on inclined plane can automatically come down, the weight on inclined plane can automatically slip down. Similarly, this is also weight on inclined plane, so it can also automatically come down. Now, if you think practically, it is a dangerous thing, because if you are using a screw jack mechanism to lift the car, and the weight of the car will automatically start the screw to slip down the internal threads, it will become dangerous. Car will automatically come down. Just like the weight on the inclined plane can automatically fall down, due to its own effects. Similarly, this is also here, the screw is playing the role of weight, and internal thread is playing the role of inclined plane. Internal thread is playing the role of inclined plane, and screw is playing the role of weight kept over it. So the observation is pretty simple, that just like block can automatically fall down the inclined plane, similarly screw can automatically start sliding down the internal threads. You imagine the screw like this, and that screw is going to automatically slide down the internal threads of the nut. Cool. What we do to prevent this? Somebody please come forward and tell me what
Sir,
is needed
theta
to
is
prevent
greater
this.
than theta. Phi is greater than theta.
Theta should be less than phi s. If we can prevent automatically falling down of weight, if we can prevent automatically falling down of weight in an internal thread, then we say that the power screw is self-locking. It doesn't self-automatically move. Self-locking means that it can lock itself from moving unless we apply a force. Self-locking means it's not going to move automatically. Okay. So let me just now write this next observation. Observation number 1, torque required to raise or lower the weight W at mean radius is this much, but we applied the torque F into A. We applied the torque F into A, but torque applied must be equal to the required torque, and torque applied must be equal to the required torque. Okay, torque applied must be equal to required torque. So once we say torque applied must be equal to required torque, we get this whole result for F. Now, observation number 3. Observation number 3 is that for the weight not to automatically slip down, for the weight plus screw not to slip down the internal thread, not to slip down the internal thread by itself, angle of thread must be less than phi s, and phi s is written as tan inverse mu s. Phi s is written as tan inverse mu s. Is that clear? So how we write phi s? Phi s we calculate as tan inverse mu s. This is called the condition of self-locking of screw. We call it the condition of self-locking of screw. This is the condition of self-locking of screw. This is the condition of self-locking of screw. Keep this in mind. Then, in our initial version, theta was the angle of inclined plane. How do we calculate theta here? In our initial version of the rehearsal of power screw, of the drama of power screw, of the some kind of mock power screw, theta was the visible angle of the inclined plane. But here, theta is not really going to be visible to you. You are going to express theta in terms of few other things. And what are those other things? My dear friends, we can calculate theta very easily because we know that our movement is some fixed movement when we complete one rotation. You start here, start here, and go back and back, go back, go back, and then you finally emerge. Go back, 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 and finally you emerge here, and then after you complete one rotation, my dear friends, you reach here. This amount of axial displacement completed after one rotation is called as lead of the screw. This amount of axial movement that you complete after one complete rotation is known by the name lead of the screw. And how much is the horizontal movement you needed to complete this much vertical movement? How much is the horizontal movement that you completed to achieve this vertical movement? To achieve this vertical movement, How much is the horizontal movement that you completed? Tell me.
Sir, 2 pi r.
The 2 pi rm, exactly. So corresponding to 2 pi rm horizontal movement, the vertical movement you achieve is L. Corresponding to 2 pi rm horizontal movement, vertical movement you achieve is L. Can you please now tell me how would you calculate that what angle you are making from horizontal?
Tan theta
Tan
equal
theta
to L by
equal to L by 2 pi rm.
L upon 2 pi rm. L is called what? L is called what?
vertical displacement.
Lead of the screw.
Lead of the power screw. Exactly. L has got a name, and that name is lead of the power screw. So when your horizontal movement is 2 pi rm, then vertical movement is equal to lead. So I can very clearly see that if horizontal movement is 2 pi rm and vertical movement is L, then my dear friends, theta I can calculate simply as tan theta is equal to L upon 2 pi rm. Tan theta is equal to L upon 2 pi rm. That's it. We are done. This is all about power screw. Of course, we will need one or two more things, but that we will do through problems. Those one or two more things, like efficiency of power screw, we'll do those things through problems. Chalo, so let's go ahead and try solving some problems based on this. Tell me. Tell me, people. What is the score?
Sir,
18, sir.
18.
18.
Huh?
18.
18th problem of chapter friction and applications. Suppose there is a power screw. Suppose there is a power screw with mean radius. Suppose there is a power screw with mean radius 100 mm and between internal threads of nut and power screw, the coefficient of friction value is 0.4. Then determine the condition on lead of power screw. Determine the condition on lead of power screw. Actually, this 100 mm is too much. It will become 100 mm radius. Screw means dia will become 200 mm. It will be this bigger screw. So let's take 24 mm as the mean radius of power screw. Now, determine the condition on lead of the power screw. Determine the condition on lead of power screw, lead L of power screw for the screw to be self-locking. For the screw to be self-locking, determine the condition. Determine the condition on lead of power screw for the screw to be self-locking. Acha ji. So for the screw to be self-locking, what is the condition that we know? For the screw to be self-locking, we know that theta should be less than a limit. Otherwise, what will happen? Otherwise, weight will fall by itself. Theta should be less than some limiting value. Otherwise, weight will fall by itself. So for the screw to be self-locking, for the screw to be self-locking, For the screw to be self-locking, theta must be less than pi s. But I don't know how to calculate theta. I rather know how to calculate tan theta. I rather know how to calculate tan theta. So I'm going to just operate this condition by tan both sides. That if theta should be less than phi s, tan theta should be less than tan phi s. Tan theta should be less than tan phi s. Tan theta, just now I told you, if you remember, that when we are moving a horizontal distance of 2 pi rm, then corresponding vertical movement is L. When we are covering horizontal movement of 2 pi, horizontal movement of 2 pi rm, then corresponding vertical movement is L. Then what will be the corresponding value of helix angle or lead angle of a screw? The lead angle of a screw, tan theta, can be written as L upon 2 pi rm, L upon 2 pi rm, and you know tan phi s. Multiple times we have written tan phi s as mu s. So tan phi s can be written as mu s. From here I get L must be less than 2 pi rm multiplied by L must be less than 2 pi rm multiplied by mu s. Lead must be less than 2 pi. Rm value is known to me 24 millimeters. 24 millimeters, and mu s value is known to me 0.4. If you want the screw to be self-locking, the lead of the screw should be less than one certain value, and that certain value is it should be less than one certain value, and that certain value is ये क्या हुआ? That certain value is 2 pi into 24 into 0.4, 60.3186 mm, 60.3186 millimeters. If you want the screw to be self-locking, then the angle of the lead angle of the screw should not be much more. Otherwise, what will happen? Otherwise, weight will automatically fall down. Cool? Let's move on to the next problem. Let's move on to the next problem. There is a power screw. There is a power screw, and we know the mean radius of that power screw. Mean radius of that power screw is just like previous one, 24 mm, and lead is given as 50 mm. Lead is given as 50 mm. Mu is given as 0.4, and there is a lever. Lever arm is given as lever arm length. Lever arm length is given as 100 mm. Determine the force required. Determine the force required at end of the lever to raise weight of 10 kilonewton. So there is 10 kilonewton weight that I need to raise. using this power screw. There is this power screw. And that power screw has got some threads. And these threads are fitted into an internal thread. These threads are fitted into internal threads. And we need to raise a weight of 10 kilonewton. 10 kilonewton. With the help of what? With the help of this power screw and a lever. And we are applying the force at the end of the lever. We need to calculate this force. By the way, the lever arm length is given to you, and the lever arm length is how much? The lever arm length is given to you as 100 mm. Perfect. So this is actually put the formula, get the answer type problem. Put the formula, get the answer, put the value, get the answer type problem. Because you already know that the torque that you are applying is F multiplied by 0.1. And the torque that is required to raise the load is W into Rm multiplied by tan phi s plus theta. Tan phi s plus theta. So F will become equal to W is given to you 10,000 Newton and Rm is given to you 0.024 meter. 0.024 meter. And then we have tan phi s plus theta. This divided by 0.1. This value divided by 0.1. Now I need to calculate this phi s and theta value. I somehow need to calculate this phi s value and theta value. You know, phi s value is the limiting angle of friction, and that can be calculated by mu s. So because I have a mu s value available, mu s value is 0.4. So this is going to become 10 inverse 0.4. This is 21.80 degrees. 21.80 degrees. And then, my dear friends, we have this theta value. Theta value, how do we calculate? Theta value we calculate as lead of the screw upon 2 pi Rm. I say it once again that for a horizontal movement of 2 pi Rm, there is a vertical movement of axial movement of the screw, and that axial movement is called as lead of the screw. That axial movement is called as lead of the screw. So let's put the lead value as 50, and let's put the RM value as 24, and I'm going to get tan theta is equal to 0.33157, and then tan inverse of the answer 18.34 degrees. 18.34 degrees. So now I know the theta value and I know the phi value. I can put those values here. I have F is equal to 10,000 multiplied by 0.024, 0.024, and then tan phi s plus theta. Phi s is how much? Phi s is 21.80. Theta is how much? 18.34. Tan phi s plus theta upon 0.1. Somebody please calculate this value and tell me how much force will be required to raise this
20
load.
24.24.
24.24. Now, notice that why this is called a power screw. Because you are raising a weight of 10 kilonewton, 10,000 newtons, and you need to apply a force of only 2,000 newtons. The output is 10 kilonewton, and the input is only 2,000 newton. With a proper design, this can be even further reduced. With further proper design, this can be further reduced, my dear friends. Okay, so we need to raise a load of 10 kilonewton. We need to apply a force of only 2 kilonewton. 2 kilonewton force needed to raise the load of 10 kilonewton. Now that prompts us to calculate something called efficiency of a power screw. Then how much is the work input we are giving and how much is the work output we are obtaining? How much is the work input we are giving and how much is the work output we are obtaining? Let's define something called efficiency of the power screw. Let me remove only this part because the diagram will be needed. Even you remove this F is not really needed because we are not, by F, we are not really doing anything. We are producing same torque as the torque actually required. So what work really is being, F into A is doing the same thing that is actually required at mean radius. So what is the work really that you are doing? Your torque required to raise the load is how much? Torque required to raise the load is how much? Torque required to raise the load is W into Rm and tan phi s plus theta, isn't it? So how much work are you doing? How much work are you doing? You know, work done is nothing but how much work input you are providing. The work input that you are providing is very clearly torque multiplied by angular displacement. Torque multiplied by angular displacement. Torque multiplied by angular displacement. Let's say torque is anyway known W into Rm and tan phi s plus theta. W into Rm tan phi s plus theta. Torque is known. what is the angular displacement? Let's say we are doing n number of revolutions, then angular displacement will become 2 pi, and then again 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 2 pi. So let's say we are doing n number of revolutions, and if we are doing n number of revolutions, total angular displacement will become n multiplied by angular displacement in one rotation or one turn of the screw. N is the number of turns, n is the number of times a screw has been rotated to lift the load, and 2 pi is the angular displacement in one rotation or one revolution. So my dear friends, we get work input from here, and that work input is going to become W load into Rm, W load into Rm multiplied by tan W load into Rm multiplied by tan phi s plus theta, further multiplied by 2 pi n. What is the work output you are producing? What is the work output you are producing? Tell me. What is the work output you are producing? Work output is the force into linear displacement that is given to the force. Force into linear displacement that is given to the force. So there is a force, and then there is a linear displacement that's given to the force. How much is the linear displacement if you are making n number of turns? Who will come forward and tell me? If you are making n number of rotations, n number of revolutions, n number of rotations or n number of revolutions, who will come forward? If you are making n number of rotations or n number of revolutions, then how much is the linear displacement that weight will undergo? Somebody please come forward and tell me. This is easy. This is really easy.
Sir, W into lead.
If is the lead.
Linear displacement is how much?
Sir, lead of the screw.
That's it.
No, sir. Number of lead covered.
You're saying it correct. Say it again in an explicit manner.
If L is the
In
lead
one
of the
revolution
screw,
of a screw, how much axial
N-
displacement a screw is having? In one revolution, how much axial displacement a screw undergoes? Equal to lead.
Yes,
When
sir,
you
lead.
rotate a screw, it keeps moving now. When you rotate a screw, it keeps moving now. So in one complete revolution, it covers axial displacement equal to lead. So in n number of revolutions, how much axial displacement
Sir,
will it
N into
cover?
lead, sir. N into
N
lead.
into lead, exactly. In one revolution, my dear friends, in one revolution, axial displacement is defined as lead of the screw. Axial displacement is defined as lead of the screw. Then in n number of revolutions, how much will be axial displacement? In n number of revolutions, axial displacement would be in n number of revolutions, axial displacement would be n multiplied by L. N multiplied by L. Now you know work output. Now you know work output. Work output is W multiplied by N multiplied by small l. Now, can you calculate efficiency? Yes. So what's going to be the efficiency now? Simply work output upon work input. This is the way we always calculate efficiency. Output upon input. So now I know the output and now I know the input. So I'm going to have output upon input defined as the efficiency. Output upon input defined as efficiency. ध्यान से समझियो. So now we know the output work and we also know the input work. We can go ahead and we can define efficiency value. What will be that efficiency value? Efficiency value will be work output upon work input. Work output is how much? W multiplied by N multiplied by lead. And work input is how much? Work input is W into Rm tan phi s plus theta into 2 pi n. W into Rm tan phi s plus theta multiplied by 2 pi n multiplied by 2 pi n. Now you see W will get cancelled and now you see N will get cancelled. And you tell me L upon 2 pi Rm is representing what? I can't see L upon 2 pi Rm. I will show you. L
Tan theta.
upon 2 pi Rm is representing tan theta, exactly. L upon 2 pi Rm is representing tan theta. So L upon 2 pi Rm is representing tan theta. So we are going to have tan theta in numerator and we are going to have tan phi s plus theta in denominator. Tan theta in numerator and tan phi s plus theta in denominator. This is the efficiency formula. So if you know the leads and you know the mu-s value and you know the mean radius, then you can calculate theta and phi s. And once you calculate theta and phi s, then you will be able to calculate the efficiency. Mug this formula. Mug up this formula, mug up this formula, mug up this formula. Make sure that you remember this formula. As the 20th problem of the chapter. As the 20th problem of the chapter. Let's say there is a power screw and that power screw is having a lead of 40 mm, a mean radius of 20 mm, a mean radius of 20 mm, and mu-s value of 0.3, actually 0.4. I just need to calculate that the screw is self-locking. It is self-locking. Determine the efficiency of this screw. Very interestingly, efficiency of the screw is independent of the load that you are lifting. That means the ratio of input force and output force will remain fixed. Ratio of, for a given power screw, ratio of input force that you need to apply at mean radius and output force that you are lifting, that ratio will remain fixed. Okay. So very interestingly, the efficiency of a screw is independent of how much load you are lifting. How much is the efficiency? We already calculated. Tan theta upon tan phi s plus theta. Tan theta upon tan phi s plus theta. Now, if you remember, tan theta is again for horizontal movement of 2 pi rm. The axial movement of the screw is L. So theta can be calculated using the formula tan theta is equal to L upon 2 pi rm. L is given to you 40 and L is given to you 40 and Rm is given to you 20. So this becomes simply 1 upon pi. This becomes simply 1 upon pi and I get now tan inverse of the answer is 17.65 degrees. So theta is now known 17.6568 degrees. 17.6568 degrees. 17.6568 degrees. And now let us calculate the phi value. And now let us calculate the phi value. Phi value is calculated as tan inverse mu s. Tan inverse mu s. And mu s is given as 0.4. So 21.8014 degrees. 21.8014 degrees. Okay. Now I can go ahead and calculate the efficiency. Efficiency will become tan 17.6568 upon tan theta plus phi s plus theta 21.8014 plus 21.8014 plus 17.6568. Now you calculate this value and report what exactly are you getting. Plus 17.6568 and then tan of the answer is this much and tan 17.6568 upon answer is 0.3867, 38.67%. So the efficiency of the screw is 38.67%. This given screw. Of course, it's not very high efficiency. So we would like to know, is there some condition existing? Is there some condition existing for maximum possible efficiency? Is there some condition existing for maximum possible efficiency? Okay, efficiency of a given screw is fixed. But can we do something to have that fixed value as great as we want? Can we really do something to have that fixed value as great as we want? Can we do that? Let's try. Let's try. This efficiency value is not very high. And we would certainly like to know if there is anything we can do. If there is anything we can do to have as maximum value of the efficiency as possible. Let's see. Let's check. So as our next problem, we are going to check this only, that find maximum possible efficiency of power screw. Find maximum possible efficiency of power screw. Okay. So let's find maximum possible efficiency of power screw. We already know the efficiency formula. Efficiency formula is tan theta upon tan theta upon tan theta upon tan phi s plus theta. I'm just going to change it into sine and cos, because at least sine and cos have some maxima available. Dealing with tan is not going to give us any clue. So I'm just trying to change it into sine and cos so that we can think more clearly when we think about maxima and minima. So let's change it into sine and cos. That will become sine theta upon cos theta, and this one will become sine phi s plus theta upon cos phi s plus theta. So that cos phi s plus theta will go to the numerator. Now let us introduce 2 in the numerator and 2 in the denominator. So I'm going to get 2 sine theta and cos phi s plus theta. And in the denominator, I'm going to get 2 cos theta and sine phi s plus theta. Two cos theta and sine phi s plus theta. Now, if you already know, great for you. If you don't know it from today, that 2 sine A cos B can be written as sine A plus B plus sine A minus B. 2 sine A cos B can be written as sine A plus B plus sine A minus B. Sine A plus B plus sine A minus B. Yes, so we have sine A plus B and we have sine A minus B. Similarly, and this is something that can be obtained very easily. Sine A plus B is sine A plus B is sine A cos B plus cos A sine B. And sine A minus B is sine A cos B minus cos A sine B. Now, if I add them together, then second term will get cancelled and I will get sine A plus B, sine A plus B plus sine A minus B, sine A plus B plus sine A minus B, and on the right hand side, I will get 2 sine A cos B. On the right hand side, I will be getting 2 sine A cos B. Okay. So 2 sine A cos B would be written as sine A plus B plus sine A minus B. So 2 sine A cos B can be written as sine A plus B plus sine A minus B. Let's write it. Sine A plus B plus sine A minus B. Sine A plus B plus sine A minus B. Similarly, 2 cos A sine B can be written as 2 cos A sine B can be written as if I add these two, I got 2 sine A cos B. And if I would have subtracted these two, then first term would have been cancelled, and I must have got 2 cos A sine B as sine A plus B sine A plus B minus sine A minus B. Sine A plus B minus sine A minus B, and cos A sine B and cos A sine B get added, and I get 2 cos A sine B. I get 2 cos A sine B. So 2 cos A sine B can be replaced as sine A plus B minus sine A minus B. I'm going to now replace it as sine A plus B minus sine A minus B minus sine A minus B. Theta and theta and theta and theta get cancelled. In the numerator, I get sine 2 theta plus phi s, sine 2 theta plus phi s, and plus, actually minus, because sine of minus phi s will become minus sine of phi s minus sine of phi s, and then we are going to get sine 2 theta plus phi s, sine 2 theta plus phi s, and minus minus plus sine phi s, and minus minus plus sine phi s. Now, my dear friends, we don't know. We know only one thing, that phi s is fixed for a given mu. We only know one thing, that phi s is fixed for a given mu. Now we have one way to differentiate it with respect to theta, but differentiating it doesn't help because the function is actually monotonically increasing. Now, this is something I checked, so I'm telling you, or this is something that other people have already checked. Otherwise, if you would be the beginner of this analysis, if you would be the person who started this analysis, first you will have to, whenever we are trying to maximize something, we naturally differentiate it and equate it to 0. The very first thing that we do is we differentiate it and equate it to 0. So people, the thing is that I'm telling you that I actually did it, and I found that this function doesn't have any maxima. This function doesn't have any maxima existing. Well, naturally, a function has maxima existing only if the derivative becomes 0 somewhere. Only if the derivative becomes 0 somewhere. But sometimes the function doesn't have such kind of maxima existing if the function is monotonically increasing continuously. If the function is increasing, then we don't have anywhere derivative becoming 0, anywhere derivative becoming 0, anywhere derivative becoming 0. And believe me, This function is monotonically increasing. How it is monotonically increasing? How do I believe that? You check it. You check it. You check it. You check it. For given mu s, for given mu s, phi s is a fixed value. Let's say phi s is 0.5. Let's say phi s is 0.5. For given mu s value, phi s is a fixed value, and let's say sine phi s is 0.5. If phi s is fixed, then sine phi s is going to be fixed. Let's say sine phi s is 0.5. What? Say. Now, with theta is equal to, now, with theta is equal to 20 degree, you check efficiency. And now with theta is equal to 25 degrees, you check efficiency. Now you check it. With theta is equal to 20 degree, or forget it. You have in numerator same thing present, and in denominator same thing present. And given that beta is a fixed quantity, if beta is a fixed quantity, check for alpha is equal to 0. Check for alpha is equal to 1, and then check for alpha is equal to 2. Let's say beta is 0.5. Then once put alpha is equal to 1, and once put alpha is equal to 2. If you put alpha is equal to 1, and if you put alpha is equal to 2, what are the efficiency values? 1 minus 0.5 upon 1.5, 0.33. With alpha is equal to 1, efficiency value is 0.33. And with alpha is equal to 2, 2 minus 0.5 upon 2 plus 0.5. This time efficiency is 0.6. Similarly, you put alpha is equal to 3, efficiency will become furthermore. If you put alpha is equal to 4, efficiency will become furthermore. If you put alpha is equal to 3, you will get even higher value of efficiency. So 3 minus 0.5 is 2.5 upon 3.5, and this time it is 71.43%. 71.43%. Similarly, alpha is equal to 4. If I put alpha is equal to 4, I'm going to get 3.5 upon 4.5, 77.77%. So one thing is very clear, that for a fixed value of mu, for a fixed value of coefficient of friction, for a fixed value of coefficient of friction, this whole function is monotonically increasing with increase in value of sine to theta plus phi s. By the way, this was just a demonstration, okay? Don't say ki, sir, alpha is some sine function, how you took it greater than 1. It was just to demonstrate that given function is monotonically increasing function with alpha. If you keep increasing the first term in numerator and the same first term in denominator, if you keep increasing the first term in numerator and the same first term in denominator, then my dear friends, you will have more and more and more and more efficiency values. So I'm very clear now. That if the so-called alpha value, that is sine 2 theta plus phi s becomes more, then efficiency is becoming more. So what is the maximum value that sine 2 theta plus phi s can have? Any sine function can have maximum value 1. Any sine function can have maximum value 1. And when that maximum value happens, that maximum value happens when angle becomes pi by 2. The maximum value happens when angle becomes pi by 2. So I get 2 theta is equal to pi by 2 minus pi by 2 minus phi s. I get theta is equal to pi by 4 minus phi s upon 2. If you want a power screw to give maximum efficiency, if you want a power screw to give maximum efficiency, my dear friends, if you want a power screw to give maximum efficiency, keep the lead angle of that power screw as pi by 4 minus pi s upon 2. Keep the lead angle of power screw as pi by 4 minus pi s upon 2. Keep the lead angle of that power screw this much. ध्यान से समझियो, बहुत ध्यान से समझियो. My dear friends, what is the corresponding maximum efficiency, by the way? Corresponding maximum efficiency is 1 minus sine pi s and 1 plus sine pi s. 1 minus sine pi s and 1 plus sine pi s. 1 minus sine phi s and 1 plus sine pi s. This is the maximum efficiency formula. This is the maximum efficiency formula. Now, try understanding. Observation number 1, horizontal force required to move the block up an inclined plane is W tan phi s plus theta, where theta is the angle of inclined plane and phi s is limiting angle of friction, written as tan inverse mu s. Observation number 2. Observation number 2. The horizontal force required to move a block down an inclined plane. The horizontal force required to move a block down an inclined plane is W tan phi s minus theta, where once again theta is the angle of inclined plane and phi s is limiting angle of friction, also known as angle of repose. Observation number 3. Observation number 3, that this same formula will be used in power screw and this same formula will be used in power screw. So torque required at mean radius, torque required or calculated at mean radius, torque required to raise the load or lower the load will become W tan phi s plus theta and phi s minus theta, W tan phi s plus theta and phi s minus theta. Of course, it's the force, so you must multiply the force with the distance. You must multiply the force with the distance to calculate the torque required. Now, if you are applying the force somewhere at some other length, then your torque applied must be equal to the torque required. Plus sign will be applicable for raising the load and minus sign will be applicable for lowering the load. For the screw to be self-locking, there is a condition, and that condition is lead angle must be less than the limiting angle of friction, and this gives you tan theta less than tan phi s, but tan theta can be written as L upon 2 pi Rm, and tan phi s can be written as mu. So for the screw to be self-locking, lead of the screw must be less than 2 pi Rm into mu. Observation number 7, that for a horizontal movement of 2 pi Rm, there is a vertical movement of screw happening, that is L. So theta can be calculated simply as tan theta is equal to L upon 2 pi Rm. Tan theta is equal to L upon 2 pi Rm. Observation number 8. Efficiency of the power screw is defined as output work upon input work. Output work is weight that you are lifting multiplied by the axial displacement into number of revolutions, and input work is torque that you are applying multiplied by angular displacement into number of revolutions. If after you simplify this, you get finally the result tan theta upon tan theta plus phi s. Tan theta upon tan theta plus phi s. My dear friends, maximum possible value of this efficiency is 1 minus sine phi s upon 1 plus sine phi s. And this is possible when the lead angle is pi by 4. When the corresponding lead angle is pi by 4 minus phi s upon 2. Pi by 4 minus phi s upon 2. This is the whole story of power screw. Observation number 1, observation number 2, observation number 3, observation number 4, observation number 5, observation number 1, 2, 3, 4, 5, observation number 6, observation number 7, and finally observation number 8. That's it. We are done with the power screw. Next class, we'll do wedge friction. That's tomorrow. And we'll wind up a big chapter called friction and applications.
Sir,
And next class at 2 p.m., we are going to do probability. And today we are going to do many problems in many questions in the chapter probability. Thank you so very much, people. See you after lunch. Go have your lunch. Anything you want to ask?
sir, efficiency is equal to tan theta by tan of theta plus phi s. Is it applicable for theta less than phi s or theta greater than phi s?
No, theta less than pi s naturally. You are always going to do every analysis for screw to be self-locking. If screw is not self-locking, that power screw is useless.
Yes, sir.
if a screw is not self-locking, that power screw is useless. So our entire analysis we have done is actually for self-locking power screw. अरे एक तो ये select ही नहीं होगा. I just want it to be neat in PDF, but no. Why this lowermost part is not getting selected? Leave it. Okay, people. Bye then. See you in the